record button, then yeah. Just let me know if you can't see or something because. Okay, guys, so this is our schedule for the rest of the semester. I didn't actually post the mom slides. But anyway, the students already they were working on the problem, so it's fine. Today we're doing power factor. It's going to be online, and I think the next week we will do resonance, which is basically the end of RLC circuits, and then we'll start on three-phase. Then I want to do the following, hopefully the following session, which is the 20th of April. We can have that hopefully on campus, and then hopefully the three-phase and AC motors. Then hopefully we can do on the 30th of April on that Friday, hopefully on campus. I don't know, we have to just kind of figure that out, either online or campus. But the last session will definitely be online, which is the 3rd of May. But yeah, so let's see the schedule. And then I think my plan here, right? I just want to share with you guys. I'm not sure if I should actually sorry about this. If I should have how do I say? So like take test 2. I wanted to, you can actually see I wanted to do DC machines and stuff. So I'm gonna place this here. Because anyway, I might shift test 2 there to the 3rd of May. Can you guys see that? Then it'll cover power factor, resonance, three-phase, and AC motors basically. Yeah, I think this can actually work, students. What do you guys think about that? At least for this particular subject, I think this is possible. Guys, can I get some? Are you guys tired or what? Thank
Yes,
you,
I think
Casimiro.
so. At least it will give us more time to study.
Yes, and the 3rd of May is on a Wednesday. So I'm obviously trying to, like I said, I always work in the best interest for my students. So at least in the mom, I'm just trying to push the one test, in the other week. Where's my phone? I don't know. I don't know how the dates look. I can roughly recall. Obviously, I wanted all my tests in the last week, but that's the only thing I can do on my end, guys. I'm being honest with you, because otherwise I won't end up covering all the content. So I can shift the test a week early. I'm telling you now. So you can actually just present. You see, the thing is, why do I have the 3rd of May? Oh, it's Mr. Lavita's test as well. So that's another problem. You know what I mean? He has the 3rd of May as well. So I don't know, guys. I don't know what to do. Because I can't have it any more time before that. It's just not going to work out for me. And alternatively, maybe on the Friday, I can have the test on the Friday. Yeah, the 5th of May maybe. Guys, are we all there? Can you please just, on 6th of May, sorry. It's a Friday. When you guys write your legal knowledge test, can you confirm with me? So we can just, I'm trying my best to sort this out for you guys now, so I can make any arrangements now before I decide on whatever. So let's do it on Friday. Guys, please, man. So 2 chapters will be, what is? So 2 chapters will be learned. Mr. So what happened to your English? 2 chapters will be learned between test and final. No, it's just transformers. It's just 1 chapter before the final. That's typically how it's done. Yeah, it is tripping drastically, yes. 1 chapter before final. Transformers. Mr. Duplessis, are you happy? Sounds good. Okay. That's the best I can do, guys. So I need to change it to probably a Friday or something. Then you're writing on the 3rd, and then the 4th, and then the 6th, apparently. So that's what. See, guys, just hold on. If you have if you look at the dates here, it's 3, 4, 5, 6. So I really don't know. Can you please help me here? because I have set my date, so they already discussed 3, 4, 5. So my words are like, I don't know what to say. It's too tight. History is two. So guys, I honestly don't know what we're gonna do here. You see, mom is the 9th. Yeah, I got it. I got it here. Thanks, Johan, for sending it to me. But I mean, I wanted to just post it. It's. I don't know, guys. It's just. Yeah, it's just I don't know. I really don't know. I mean, it's just too tricky. The 6th is the Thursday. I mean, the Friday. So. Okay. Anyway, I'm not really sure. This will require some thinking, right? So we don't know yet. We need to figure this out. The actual date planned was then it was the 11th. Or not the 11th. What was it again? What was the date before this? Let me just go back. 3rd of May. No, I'm not sure. Oh, sorry. It was the 11th of May there. Yeah. So that is what it was. And it's a clock. I mean, you guys should be fine. Just that I don't wanna, you know, if you guys can come with an alternative plan, I'll be happy to try to accommodate you. But what is key is just that I complete these chapters. So by this week at least, because I mean, this is just like a follow-up chapter. And again, electrodes is easy. It's not difficult. And also your assignment, I did not actually put here. So I'm probably going to give you assignment here in this week. Assignment 1 and 2. I'll give you both assignments one time. And I will give you by next week. Just trying to figure something out on my assignment in terms of that. And then you can submit. When can you submit? Actually, I want you to submit. Yeah, submit on this date. So you have. Let me just look for a reasonable date here. Yeah, the 13th of May when you close. Yeah. Cool. 13th of May. So I'll give you both assignments worth. It's gonna be total 10%, and it's actually. It's supposed to. I'm gonna be. It's not that difficult to do. It's just a bit of work. It's actually quite easy. You can literally finish it in a few days. So I'll give you. Just checking on my phone quickly. So I'll give you like more than enough time. So that's the 13th of April. Yeah, let's say the 13th of May. This week, yeah. That's basically the week, the study week. Yeah, cool. So I'll obviously focus on LP Spice, like I said, and like I said, I probably wanted a group assignment, so just to be easy to mark. You know what I mean? So yeah, guys, we have obviously this is tentative now, right? But are you aware of the assignment now? Are you guys content? Is there any questions before we begin the official lecture? 49 slides, hectic. So actually 49 slides, some exercises in these well. Any questions, students? No, we don't know. It's not that. That is it's very precarious now. It's quite uncertain. Like I said, if someone can come with a good plan, then yeah, sure. 11th of May was the day I initially gave anyway, so I'm just, yeah, I'll have to figure it out. Okay, I think we've had enough of this. So I'll just actually start the lecture. So guys, we are starting on, we'll be doing chapter 7. That's power factor. Where is my textbook? Oh, yeah. Chapter 7. Yeah, cool. So that's page 7.1 if you are going to follow the textbook. All right, so let's begin. So guys, we looked at power of DC circuits, right? You guys remember we did this question in the first, we returned from, we just started S3. And can someone please tell me the power for a DC circuit? Quick. What is the formula we typically use here? Sorry about that. I can't. Yeah. V times I. Thank you, Mr. Silver. So we typically use P equals VI, right? And what I want to mention with regards to this is I mentioned to you that this will have the total power. So for argument's sake, let's say this was giving out 60 watts, right? Just hypothetically. And it'll distribute depending on the resistance value each power. So let's say this was 30, this will be 20, and this will be 10 watts, right? And we know that all the power must basically equal to the source's power, right? I think we're all aware of this. So it's important to understand how all of that works. So what we're going to be doing today, the chapter is called Power Factor, but the question is, so what about AC circuits, right? My question to you, can we still use P equals VI? Can we? Can someone tell me, is it possible? I would love to have this lecture on campus to see, to get someone. So guys, can we use power equals Y? Yes, Ryan, just want to tell me why can we use VI for AC circuit? Why can we use it? Yes, that's a good question. If the power factor is 1, rather, that's very important. Nicely said. If the power factor is 1, it's a historic power factor. That's a very important part there. Yes, we can use that formula if. Okay. So what I want to tell you, so with AC circuits, right? The only difference is, right? So we can't actually just use VI, right? It's not possible. And the reason why is, like I said to you, the voltage is changing, right? And in a resistor, we find that the voltage and the current, they are in phase, right? So we can actually use power equals, right? That doesn't look like it's in phase, but in phase, right? That's supposed to show it's exactly the same. Now in inductor, right? Remember over here, the current will lag, right? So it's out of phase. So remember we did some stuff in AC circuits, right? So it lags, whereas in a capacitor, it leads. So what we have here, right, is a phase difference. Oh, just for that. A phase difference or phase angle difference phi. This would be negative, that would be positive, right? Remember when we were doing the AC circuit analysis, we found out there was this, will it be a leading or lagging circuit, right? So remember, and when we did a question like this, we normally came out the current at an angle, if you remember. What that angle was, so let's say, remember for this particular question, that was figure 6.10. My students, are you following my logic here? It's very important that you follow my logic or my explanation here. Students, are you good? Oh, total. Yeah. Thank you, minutes. Thank you very much. Yeah, if it isn't one, yes, okay, this is what I'm going. Thank you very much. So what I'm saying is that for that particular problem, just give me a moment, our total current was 10.23 at an angle of minus 9,19 degrees, right? This is just for that particular problem. It's not a big deal. What this means, what this 10,23 minus 9,19 means is that the current is 9 degrees out of phase compared to the voltage. And obviously, it will look like this. Obviously, not that I expect you to sketch it. Okay, now let me just use the same as what I had before. And that's what that value means, right? That's the voltage, and obviously, you just get the current. So there's a 9-degree difference, basically. There's a 9-degree difference here. And that shift between that angle between the two graphs is what the power factor is, basically. And obviously, you can obviously there's still a lot more than that. I'm just giving the overview here of what you're trying to do. That angle now, that is what we call the power factor, if you've ever wondered what it was. And what it means that we can't just use P equals VI, right? It's not that simple. We can't use P equals VI. So we are going to use P equals VI, right? So I can say P here equals VI. And what it means is that we need to include phi somewhere, right? We need to include that angle, basically. So and obviously that angle, and we're dealing with sine and cos, or sine waves, it's going to be some kind of trigonometric function here, trig function at some angle. So this is just a general overview before I start going. I'm actually starting the lecture, but I want you to understand that because you're dealing with AC circuits, yes, for resistance, we can use VI or I squared R. But when we come into inductor and a capacitor, because of that phase difference, that phase angle difference between the voltage and the current, we now need to incorporate that within our equations. So clear, students? You guys, can I just get a thumbs up there if you guys follow that? That is what we're essentially going to be doing. Any questions? Thank you very much. I appreciate that. Everyone else is on the same page. It's just the holistic perspective of what we're trying to achieve. In terms of this particular thing. It's not difficult, it's actually easy, just that I'm giving you some background on, trying to give you some background at least. Okay. So another chapter, obviously, I like to use John Bird as well for your further enrichment. Check power, chapter 26, power and AC circuits. It has obviously more problems and different situations which you can exercise yourself in, but it all goes down to the same fundamental concept in terms of what you're going to be doing. So I'm just putting that there so I can let you know. Cool. So I got some data plates from various things over here. And I'm sure you guys have seen, these are from all typical electrical machines, induction motors, transformers. Here's an AC generator, for instance. We can see power factor on the data plate itself, 0.8, 0.81. If you look at this ground force, that's typically pumps. Even this has a power factor. Can you guys see it there? This is depending on how you run it. You obviously got a star and a delta symbol, which we'll be touching on the next two sections. Talk about that again, is how you wire it. Can you see the power factors there? That cause phi. I'm just showing you, like holistically. Can you guys see it there? It's a number which appears on the data plate actually, right? And let me just shift this guy around. Just want to open this up. Make it bigger for you. So on all electrical machinery, you actually see the power factor. How can you guys see this? There's another classical one. Can you see there your frequency? And then over there 0.92. Can you guys all see power factor? So before we start this power factor chapter on this particular slide, I would like to ask any student or any students the experience with power factor, what they know about power factor, and any experience on board with particular power factor. So I'm opening the floor, and you can just engage if you have something to share. Pick some names: Mr. Ford, Mr. Biavanga, Mr. Nkita. Anything, Tashriq, anything about power factor, any experience with it or your understanding of it. Can you guys still hear me? Parimang, Mr. Sima. The Bisama showed you, I can see your name there. Any experience, guys? You have no experience with power factors, thanks. Nope. Okay, cool. So anyway, making aware it's an important parameter on all electrical machinery essentially. Yeah, so that's fine. Okay, so this is what I was essentially talking about, and this is a picture of 3 waves. Okay, someone's saying something. Oh, okay, you say something useful. Yeah, you says just when filling the logbook, you note the power factor of a running generator. Fantastic. That's very important. Yeah, there we go. There we go. Thank you for bringing it. So that's why it's a value. So now you're writing down the value, but the question is, what is that value, right? Obviously, when we do singular generators, you obviously see how it will change. But thank you for it's a value you need to understand. Thank you very much. So there we have 3 different voltage waveforms, voltage and current waveforms. And obviously we all have experience now, a pure inductor, 90 degrees out of phase, and a pure capacitor, it's leading. And as you can see, what we're essentially looking at is just 2 waves there, right? So and we want to basically somehow add the waves with somehow, with some method. So what they're saying there is that the value of any instant power is the product of your voltage and your current, right? So we know this, and it's shown by the broken line. So it's the the lines with the spaces in between them. So that's roughly the average power. And you can see there's basically kind of like no power in the capacitor, the thing that's according to them. It's difficult to actually find that. And what happens is that this is now a waveform for typical or a resistance and inductor circuit where your voltage obviously you can't lags the voltage. And they're saying the waveform for the power where P equals VI is shown by the broken line here, and hence the power, the average power, right, which is it depends on the value of that angle phi, right? Which is the spacing between the two waves. So if you have a look at the sketch, you've got your voltage, your current, and there's obviously the average power. You can see how they drafted there. And it's going to depend on the phase difference between. Obviously, I mean, I'm not explaining the first part again, obviously in my own way. And that phase difference, well, the cause of the phase difference. So I haven't done any maths here. So all you have to know is that power in an AC circuit, right? It's going to be VI cos, is that alpha, was it phi, PHI, that circle the line through, right? So, and like I said, it's a function of the phase angle there. And saying there, oh yeah, they say phi is the phase angle between the current and the voltage. Where V and I are understood to be the effective RMS values. Very important. So always remember, like I said to you, the values we work with are root mean square values, right? It's not perfect sine waves here. And then they say that the term cos phi is called the power factor. So all it is, it's still the same formula, but all we have is a cos phi on it, and that phi is just due to the shift, the different phase changes in obviously for resistor, because in phase we still use VI, but for inductor or capacitor we use VI cos phi. If it is phi, yeah, or theta, whatever. Now I made a note there, just as a special thing, and you actually take this and paste it somewhere else. So I wanted to talk about it before, but I thought, okay, let me just paste it at another place. Okay, it was there. Where was my active power? Okay, I'll keep it for now. Cool. So yeah, so that formula over there, if you guys can see it, is a new formula, which is basically you're gonna have to learn, or one of the new formulas. Excuse me. Cool. So now AC power, what actually happens, right? So let me just give you a holistic perspective of what happens here. So when you, for instance, what you're not seeing there, it's supposed to be shown, well, rather. So you get three different kinds of AC power. So this is the power we know in watts. But what is this watt? So is that the only power? No. So what do we actually have? So what actually happens is that your supply, right? Well, supply the let's say you're either getting from a generator or from your wall socket, or you plug into the mains, basically, that the generator will give you VI, right? S times VI. So if you look at a typical generator, it will be rated in terms of kilovolt amps, or even the transformer. And what it is that is the actual electrical power supply. As you can see, it's VI, the traditional VI that you actually know, right? It's the same, like the power equals voltage. But then what happens is that your apparent power will now split into two components, which is the active power or true power. The true power and active power is what you know, the VI cos phi, which is in watts, and your reactive power, which is a new thing. It's a bit vague, obviously. What is the reactive power? So the apparent power gives birth to two kids. One is useful and one is basically useless, right? Arguably. So yeah, the same. So if you're running a motor, for instance, they say for it to function properly, it needs two powers. Did I hear someone say something? The reactive is a loss, yes, that's correct. Arguably a loss, which I'm saying. It is a loss in terms of. So if you're running a motor which is typically inductive, because obviously you're running electromagnetic inductions, a magnetic field, conductors crossing the magnetic field, etc., etc. The active power component, right, is the what actually performs the work. Meaning that's what's driving the shaft. So if that is coupled to a pump, that is pushing that. If that is coupled to a compressor, we are only getting the kilowatt. That's from the apparent power. The red in this particular diagram is what we get. Now the reactive power, as Mr. Ford said, is a loss, but it's not a loss in terms of where it actually goes to. So where it actually goes to, what it actually is, your reactive power is actually the power required to maintain the electromagnetic field. So that is actually responsible. So of the VI, a portion of it, which is in this case VI sine phi, the reactive active part, is basically making sure the magnetic field stays alive. And whilst the magnetic field stays alive, you're actually producing that allows you to produce the kilowatt. So as I state, the acting power and this active working power and the active non-working magnetizing power, and they're saying that the active power performs useful work, and that is what we focused on, the kilowatt per watt. But the active power does not. So the active power doesn't provide any work to us. So we can't use it for any mechanical energy manipulation. Its sole purpose is to only to develop magnetic fields in inductive devices, in this case. Or alternatively, it could be also to provide the electric field of the capacitor. It's that. So what we have is that we have a pattern power, which is V times I, which is the units is volt amps. Then we have active power, which we use, which is VI cos phi watts. Then we have our active power, which is Q VI sine theta. And the way we write that is volt amps, but we have a subscript R over there. Or VA or VAR. VAR is typically fine to that. Okay, VAR, as you can see there in the diagrams. Who knew this? Did I provide a new revelation? Or maybe not. Can I get some excitement? Who's learned something already? Brand new, huh? Should know this for orals. Oh, cool, man. Thanks, Rutherford, for saying that. Okay, anyone else want to chip in? So now that's the actual difference. So, right, generator gives VI, we get the power, and splits into two components. Interesting concept. Thank you, Zinkita. So the active power, yes, it is useless, but it's actually there to keep the magnetic field active, or the electric field in terms of the capacitor. And I think that picture already describes it quite nicely. The pattern power, there's two components, and then it kind of gives off. And this just to show you nothing in life is 100% efficient, There's always a bit of friction, there's always a bit of something which is not actually, we can't use. So that is why if you want 100%, you got to give 150. You want to be a millionaire, you got to ask yourself, how do I get 3 million to become a millionaire? There's always going to be some reactive power or inertia or something, lost or whatever. Okay. Let's move on. Oh, I see I want to paste that. Let me paste it over here. There we go. So just on reactive power, as it's a small concept on its own. Obviously, I'm sure there's a lot of research being done on making sure the reactive power stays to a bare minimum. But it says it's also known as the useless power or wattless power. So there's different terminologies I just need to be aware of, right? It's for the same thing basically. And they're saying this is the power that continuously bounces back and forth between the source and its load. It's called reactive power. And power merely absorbed and returned in the load to these reactive properties referred to the reactive power. And what it is, it represents that the energy is first stored and then released in the form of a magnetic field or an electrostatic field. That's what I should have said, not the electric field, the electrostatic field. In the case of inductor or capacitor. Obviously, you learn it in lectures 1 in your capacitors, and I'm sure you're taught very well that you're aware of that particular fields. And what I like there on top, the red says, an inductor consumes reactive power, where a generator generates, and a capacitor generates reactive power. I'll say that again. An inductor consumes it, hence a motor, whereas a capacitor, so when you apply a voltage across a capacitor, and it creates the electrostatic field, it generates within the field itself. Obviously, you can go into the physics on that. So I'm just giving you that view of inductor will consume a capacitor will generate. Cool. Right. So what does it all mean? Right. So now we've talked about power, right? AC power. So now in DC we said VI, blah blah blah. And then we had a resistor, we lose some power, gives it to each one. But now we talk about this cos phi and sine phi and this VI, the apparent power or the active power, the true power. apparent power, true power, reactive power, wattless power. Obviously, they're related somehow. There's a VI, there's a trig ratio. And obviously, it stands to reason how we can somehow develop some equations or model around all of these three things. So just to talk about what power factor is, right? Obviously, we had a bit of an idea. So here, I'll give you an example here. We've got a horse. Ons doen key to drive horses. I think it's one of our hobbies. Don't know what kind of horses she stocks. And she uses the horse to basically pull a cart over there, right? But now, there's an analogy basically used for power factor. Well, one of them. I've got a few of them, obviously. And it says that here's a common analogy that compares each type of power to a horse pulling a cart. And the power you're talking about is obviously your real power, represented on the vector going to the right, your reactive power going down, and your apparent power going, which is basically the resultant of the two. Interesting, eh? The resultant. And it says that if the horse can't run directly in front of the cart, which is the case, so ideally we want the horse to run directly in front of the cart, but obviously we know that at some point the horse will start to turn. It's never going to run perfectly straight. Obviously, that is where an unfortunate whip comes in. You know, well, it can go fast actually, but it's not going to keep it straight. So maybe when the whip hits the horse, it's a very bad example, guys. I'm not in for animal cruelty at all. It would start to deviate, right? So, and it says that if the horse can't run directly in front of the cart while pulling it, then some of the horse's total effort will be lost to pulling the cart slightly sideways, right? So that's what's basically showing you there on the horse is a force forward vector and a force put perpendicular, and then it's the total movement. So obviously, if it goes sideways, the resultant movement will be at an angle, and obviously there's two components, right? And obviously the resultant of the cart moving downwards and the horse moving forward will result in the horse moving at an angle. Only the force in the direction of the movement is considered work. So only the horse itself moving forward. Remember, we want the car to move forward and not sideways in essence. But obviously, it's still moving forward even though it's going at an angle. And that's the only what we deem as work, right? So you add this forward vector. Okay, yeah. So that's the only thing. So they're saying, so you add this forward vector to the perpendicular vector, right? Which is obviously the direction of the cart, and then you get some kind of result, right? They're saying it's a classical top to tail, head to tail vector when you're adding vectors and stuff. So what they say in AC circuits, inductive components, that should have been inductors. It prevents the horse from running directly in front of the cart, right? And what it does also, it also increases the reactive power and increases the difference between the real power and the reactive power. So there's basically some angle. And as a result, the greater the difference, the real and apparent power and a low power factor. So what this could also be represented as is that power factor is a ratio between the apparent power. So it's a cos phi. So it's basically going to say cos phi. I also don't have it yet. I'm going to get to that. Cos phi is P over S, or it's the real power divided by the apparent power. That's what it actually is. So I'll talk to it again. And of course, I had to put this here because I know some of you guys can't relate to a horse running around. However, you guys can relate to a beer. And it states there on top, the power factor is the ratio, exactly what I just said now, of the kilo of your kilowatt to your apparent power kVA. What's important is ratio can be a value from 0 to 1, and it indicates how efficient an AC circuit is using electricity, with a value of 1 representing high efficiency, alternative 100%. And they're saying the third type of power is the reactive power, which causes electronics to be inefficient or inefficient, yes, you would say, and draws the ratio closer to 0 by creating a difference between the real power. Yeah. Another one is again power factor, the ratio between the true power P and the total power, apparent power kVA. Right? And then it says it's a measure of how efficiently electric power is converted into useful work. I might be asking a question on, theory marks maybe on what is the actual power factor. maybe with an example or so. So you go to the tap, you order your beer, barman pours it all the way up, and then you get a bit of foam there on top, so you're not getting bang for your buck there. You're getting more, the real power, obviously, we know the real power is the reactive power. An analogy, who's here? Mr. Garcia likes is another classical analogy. These are good old Lays, right? You buy a packet of Lays and the power factor here is definitely poor on this on Lays. The amount of chips you get and the amount of compared to the amount of air is a whole other story. Yeah, you're sitting with a power factor of who knows 0.1 or 1 or something. Yeah, that's another analogy. You buy a pack of chips, yeah, you get a lot of reactive power versus kilowatt hour. And trust me, that air, I guess I don't know why they actually, I do probably know why. I'm not going to go into it. Why they actually pump air into the chips and maybe to make the bag bigger, who knows. Cool. Then yes, just talking to the same thing, relating the three things, we get power factor equals the true power over the pattern power. And obviously the power factor is cos of phi. So again, if you look in the power triangle over there, or it basically is you take S times VA, you split into two components. The horizontal component is VI cos phi, and the vertical component is Q VI sin phi. So in fact, the resultant of the two vectors, the sum of the two vectors, the vectorial sum of the two vectors, P and Q, will give you so you can think of S as the resultant of the resultant of the Q and V. All right. Any questions before I move on? Is it well explained? Is there did I miss anything? Anything you want to possibly add before we get to the good stuff? Jim Kita, Mr. Ford, Johan, Mr. Mzunjana. Any questions, guys, before we move on? Thank you, Johan. You guys got it? Something you didn't understand, maybe? Mr. Sima, DJ? Thank you, guys. Okay. So like I said to you, all it really is that the pattern power, you split it into two components. One will be cos, that is where the cos will come from in this case, and then that is where you get sine as well, which is the active power, which is the vertical, the vertical component of that. Cool. Okay. So now, before I get into the actual, I think what I should do is come back to this particular part here. The disadvantage of power factor, or not, well, of a low power factor. Yeah, so I'll come back to this part, and then that is when you go into power factor correction. So I'll come back to that. So what we can do now is just do example 7.1. I don't want to talk too much. Rather, let's get our brains moving. Then I can always explain, afterwards. You can just take this here and move it here. Okay, cool. I'll just delete this for now. Okay, yeah. So we're doing example 7.1, and that is on page 72. You get your notepads out, and you can obviously see how we can apply this to a AC circuit now. So I've got a few examples actually. Yeah, but anyway, I won't obviously do all of them, but I'll do what I need to do. Okay. Preparing my whiteboard. Okay. Just get your notebook out and we can start practicing. I am aware you guys had a fairly long day, but yeah, you'll have your lunch. Okay, cool. So what we have here is a simple series circuit or AC circuit. I'll sketch it for you. We've got a resistor, we've got an inductor, and we've got a capacitor. So as you can see, it also forms part of RLC circuits, basically. It's all the same. It's all the same. Even the next chapter, resonance, will talk to the same type. We've got 18 ohms. We've got 125 millihenry. And we've got a capacitor here. So what I teach you guys, and okay, sorry, and obviously this is supplying a voltage, a generator or alternator at 250 volts at 55 hertz. The number of cycles per second is that. Typically 0.02, but probably 0.0 whatever. So what is our first step before we analyze the circuit? So the first question is calculate the impedance, obviously, but what is our first step typically on an AC circuit? Anyone? You guys rusty? Yes, calculate the inductance and the inductance and the capacitance first. Well, the reactance. Yes. So we need to calculate the inductive reactance, inductive and capacitive reactance. Capacitive. I don't know why I did that. That's our first step, right? So we know for our inductor, it's 2 pi FL. That'll be the first one. And if you do that, don't spend too much time on that. You go everything. You get a reactance of 43,1969 yes, ohms, right? Obviously we know this is going to be now plus, inductors plus J 43.1969, and we do exactly the same, not exactly the same, but we have to use this formula over here for our capacitor, and that's going to be 2 pi times a frequency of 55 hertz and a capacitance of 84, really small capacitor, -6, and if we get this, we will get 34.4491 ohms. Obviously, this can be expressed, and this be a negative J as a complex number. Or the imaginary counterpart is 34,4.4491 ohms. All right, so that's the easy part. Obviously, from this we can calculate our total impedance, and we know that your total impedance is going to be R. This is one way of obviously doing it. XL minus XC. And in this case, it's going to be resistance was 18 plus J 43.1969 minus 34.4491. And if you get all of that, and put it into polar form, you should get 20.013 at 25.919 degrees. You guys happy with that? Sure, you guys can do that. Yeah. So I'm not going to do all the parts of the sum, just what we need to do. So no, most students got lost in the test particularly, but they should have added all the resistors up. They didn't do that. Yeah, you add all the resistance and you have to add your capacitance and inductance. Some students actually didn't end up doing that. Okay, so what we're going to work out is the current, and we're not going to work out the voltage drop and the phase angle, because especially the voltage drop, you don't actually need to know that. But the current will give the phase angle and the power factor. Okay, so I'm going to do the current now. Because it's a series circuit, students, we know that the same current will be there. That's to be voltage divided by impedance. And a voltage in this case is given as 240. 240, and we always keep it in an angle 0. And we divide this by 20.013 at an angle of 25.919. Cool. Once we do that, we'll get a total current of 11.992 minus 25.919. All right. Okay, is everyone happy with this so far? You guys know how to do your series circuits, right? So everyone happy? Before I go into a bit of explaining here. Fantastic. Mr. Kitongo, are you following Mr. Casimiro? Oh, yes. I mean to say Mr. Garcia. Fantastic. Okay. So this is, guys, as you can see, right? Relative to our 0 degrees there, with the voltage starting, we can see that this is minus 25.919. This over here is your power factor angle. So just to give you the actual, there is that angle. So that phase angle difference is the power factor. So you're going to do the power factor, which is essentially E, question E. I'm not worried about the rest, that's all easy stuff. All you have to say, power factor is equal to cos of phi, and all you gotta say is cos. You literally can type it in the angle here. You can keep it negative 25.919. So you actually put in the actual value, not the absolute value. And if you do that, you'll get an angle of, you get a value of 0.8894. And if it's negative, and obviously when you're dealing with an inductive type circuit, right, because your current is negative, you'll say lagging. Is it clear? So what I'm saying, to calculate the power factor, you have to use cos phi, and you can put in the actual, you know, the negative 25 in the calculator, and you should get negative 0.8. But what it means that because your inductive is greater than your capacitor, and I did mention this to you before, it will be, this is either telling us leading or lagging, and obviously in this case it's lagging now, because that's the case. If XC is greater than XL, we know that this will be leading. It's a capacitive circuit and will lead the current. Is it clear to everyone? You guys get that value? So clear, students? Any questions? Oh, that's obviously the new part. Yeah, clear. Okay, that's the power factor. Did I ask you what's the power factor? You're gonna definitely have to calculate it like that. Yeah. Cool. So it's your phase angle basically there, that 25.919. All right. So once we have that, we can actually find our AC power and its components. So that's the main thing which I obviously want to look at. And that question, let's just go back to the question. And the question states there that the one true power, which is the watt full power, and that's watt, that's P, the parent power, that's S, and your reactive power. Cool. That is what I want. So remember, I'll just get it back here. So what I'd like you to do now, yourself, so I'll paste the formulas there and you'll be able to calculate it yourself. Okay, so I'll paste it here. So be familiar with these formulas because you're definitely going to get this. It's an absolute must know. And I'm assuming it's in your formula sheet. So what I'd like you to do is now you have to take the total voltage. And of course, you've worked for, you've got the total current now, 11.992, and calculate your parent power, your true power, and your reactive power. I'll give you guys around 3 minutes to do that. And you just write the answers here. So do it yourself. Say V times I, you should get the reactive power. I mean the parent power. Then do the true power, and then do the reactive power. So just give it a go. Let me know. You can type the answers in the chat if you want. Mr. Biavanga, did you get the apparent power?
Yes, sir.
Oh, great. And the true power and the reactive power? Fantastic. Anyone else get it? I just wanna obviously say a few things one time actually. Msirelelo, Msuli, Mr. Njana, have you got the power? Okay, fantastic. So discussing very about it. Okay. Guys, a simple thing, I'm not gonna write it out, but you should get it all. 2878.1 var VA volt amp. Now for your power, you typically want to always get the absolute value. So this will never be these two will always be, I think I need to check my thing. It's like, I don't know, not particularly happy. Really bothered. 25 88. Looks like it's writing slower than have to play around. 6 volts, 0.6 watts. Now your reactive power, I'm making you aware, this can either be this either can be positive or negative, right? That's very important. So typically, so here you have to put in the sign over here, right? So if you're gonna say 240 times 11.9922 sine of minus 25.92, you'll get your answer. So here you must use a sign. Use sign. Use the sign. In this case, so let me just get it open again. Where is it? Yeah. And you get minus 125.1 volt. And the negative tells you basically that it's lagging, right? So obviously, if you have a capacitor, it will be positive. So your negative reactive power tells you that it's inductive in nature, right? So this amount of energy is there to produce the electromagnetic field circuit, right? So make sure you get that. That's very important. And make sure you have the units. Be very strict for that. Okay. Another alternative way of of doing all of this, and you can use complex numbers actually, is you can say S equals V times I. All right. So what you do, you take your volts, your 240 at 0 degrees, and I want you to do this, and you times this by 11.9922 minus 25.919. Do this in your calculator and give me the two numbers. Give me the answer in rectangular form. So type this into your calculator as is 240 at angle 0 times, this is in complex mode, times by that, and then let's see what you get. Mr. Silver, can you please do that for us? Thank you, Jared. So you get 2588.63. And you get negative 125, 8.03 volt amps. And can you see that Simkita, I hope you're following this. Can you see that this is the same as that? Can you see the Simkita, Mr. Mbani, and that, oops, is the same as?
So it is blank, we can't see nothing.
And I'm trying to be cool, then it didn't work at all. Just give me a moment. Stop sharing for some reason. Okay, cool. That's probably me. So can you see your two components? The real part will give you the power. It's the same as the 2588.63. And can you see that the imaginary part gives you the reactive power? Yeah, I don't know. I was trying to show off, but it didn't work out. The kid is not even on here. Can you guys see that? With the Kitongo and Casimiro. You see that the real part gives you the true power, and then the reactive part gives you the imaginary part gives you the reactive. Mr. Jan, are you happy with the Swanepoel? With the Sozino? Mr. Asa, PJ? Fantastic. Okay, guys, so that's the end of session 1. We'll return at 14:45. I'll make it 14:50. I know you guys obviously didn't have lunch and stuff. We had a long day already. So let's return at 13:55. Lunch break. Yeah, and then we'll continue with maybe one more example of this. Then I'll talk about like multiple loads, and then obviously I'll end off with power factor improvement. Yeah, I'll see. Anyway, guys, I hope you found this first part enjoyable when you learned something, and let's meet at 13:50 for the second session. Okay, guys, enjoy your lunch. I'll stop the recording here.